So I was going back and I was creating snapshots in my VM for one rootkit change at a time. All right, don't infect anyone. You sit right there. Do you already have this book?
Oh, yeah.
All right, so the correction was I was going back and making snapshots with a single rootkit per VM because Matt asked yesterday would I eventually go over showing what the changes were actually in the system, and the answer is yes. And so I figured it'd probably be better if I made some snapshots where I put a single rootkit in a VM and then I ran the tools against it and see all the changes. So I start from a known clean VM where there's no hooks and stuff like that, and then I just put one thing at a time. So when I was doing that, I was trying to recreate this sort of change. And it turns out that I had misdescribed this probably just because I was not being particularly rigorous when I was doing my initial testing. So like I said, I thought this was due to ShadowWalker's actual hiding of a module, and that didn't really jive with what the author had said. And so I kind of didn't get it. But when I went back and looked at this, it turns out this is actually due to Futo, hiding the system process. So now it sort of makes sense because, to some degree, that 0 within the square brackets is, I believe, trying to be the process ID. And actually, that's what he's saying right here. It's saying it's PID0. So PID0 is the system, quote, process. Right? And then the address after it is an eProcess. So it's just saying the system process itself is hidden, and that's actually due to Futo, not ShadowWalker. So all is well in the world, and that makes sense. All right, so the second thing was, when I was talking about PatchGuard yesterday, I said I was going to go check if it, whether it checked if the IAT got hooked or if the IAT was changed. And the answer is no, it doesn't do any sanity checks over the IAT. Also, it doesn't look like it checks the code section for just the kernel itself, NTOS kernel or NT-kernel PA. Checks the kernel, hal.dll, and ndis.sys, which is the networking component. But it doesn't check other drivers beyond that, at least according to the quick page that I read. So that's another point, that someone could still go put inline hooks in various other components of the system, and PatchGuard wouldn't actually be stopping that. Which is, again, why it's really, I would say it's more geared towards, preventing people from using unsupported mechanisms rather than, trying to be a full-on rootkit detector. It has some elements of that, but I wouldn't say that's its primary purpose. All right, and then finally, I wanted to talk about WinDbg a little bit today because I didn't talk about it yesterday. So a couple of times yesterday I said you find a particular change. So let's say this type of change. Well, that's not a good example. Let's say yeah, the first one was actually the best one, the IDT one, which is why I sort of do this in why I have the Tiddler wiki kind of goes through this process, Tiddler wiki. So the point is, you find some change in your tool, and it's not able to help you actually attribute what's causing the change. So this is saying, IDT entry E, interrupt E is currently pointing at F9, F55, A40, which is somewhere that this tool doesn't expect it to be pointing. But simultaneously, because this happens to be pointing into a hidden module, it's not able to actually tell you what it's pointing at. I mean, it could, but for whatever reason, it's not syncing it up correctly. And so there becomes this question of how do you actually dig down into this change and find out whether it's due to malicious software or third-party software, security software, or whatever. And the answer for that is basically you have to start doing some level of debugging of inspection of the system. So I wanted to show a little bit of the technique of local kernel debugging. So some people were trying to use WinDbg because we learned about it in previous classes. So in previous classes we saw, okay, well you can really do a deep system inspection if you attach the kernel debugger, but simultaneously they knew they had to reboot the system, and some people were trying to do things entirely without rebooting. But there is a way that you can get around that and do debugging on the system while it's live without actually having to attach the kernel debug externally. So, should all go to your VM, and we're going to go download WinDebug, which I believe should not be in there right now. Yep. So we're going to download WinDebug, and we're actually going to run it from within the system. This is not the optimal way of doing things. Obviously, you want to do a normal kernel debugging session when possible, but when it's not possible, this is the next best thing. So just search for WinDebug download, WinDBG download, and go to this first link, assuming you're searching with Google. So eventually you should, if you got to the right link, debugging tools for Windows 32-bit version, there's going to be this link to install 6.11.1.404. Download that to your desktop. And then once it's there, just go ahead and install it. So I'm just going to check quick on everyone. Alright, so once the MSI file downloads, just go ahead and run it to install debugging tools. Go with the complete install. And when it's finally done, you should see in your Start menu, All Programs, Debugging Tools for Windows, and then WinDebug. Everything up. Alright, so once you have, go to All Programs, Debugging Tools for Windows, WinDebug, open that up. And then when you go to File, Kernel Debug, so File, Kernel Debug, and then there's tabs at the top, and you want to select the local tab. So normally, in the other class, we had used the COM, we had used the virtual serial port in order to debug the virtual machine. But actually, from within the VM, we can do a basic debug where it's just going to grab some snapshot of memory and then do a debug on that. And I thought the way it worked was that it literally created a snapshot, put it in a file, and then opened the file. That doesn't, I'm thinking that's not the case because last time I was playing with it and I tried to make a change and I was like, see, I can't write to memory. And then when I tried that, then it would immediately crash. So I think it is maybe having the kernel side, like, I think it's probably loading a kernel driver and there may be some basic communications between user space and kernel space here. So anyways, again, File, Kernel Debug, go to Local, and then hit OK. And then this is going to give you a basic debugging session. Alright, now as with the previous class, we need to get all sort of on the same page here. So we need to have the same UI. So you'll have this one window hovering over the gray. Drag it over the gray so that it completely fills the screen, like this. Alright, once you've got that, then so that's our command window. That's where we're going to issue commands. I think I also want to have, for this purposes, I think I just need a disassembly window. So if you see this little 1.0 in the top bar, you either hit Alt-7 or click the 1.0 there. And then you're going to get a floating window again, and we want to drag that to the middle of the right side, and then it'll split the screen like this. So drag it to the middle right. You'll split the screen and you'll have disassembly window and command window. So you've got a floating window, right? It's floating around. You drag the window to the middle right and then it should split the command window. You sometimes, if it's like overlapping, you won't be able to. Yeah, that's the thing. Okay, so now drag it down to the middle right of there. Okay, so I have a new command reference at the end of the slides. It's not going to be in your slides, but I put together most of the commands. But for now, we're just kind of hunting down this. Specifically, we're trying to investigate this interrupt E, which Gmer is reporting, and we want to see, what code is at that location, and trying to figure out if that's malicious code or whatever. So one of the commands you can use is bang IDT, exclamation point IDT, and then space E in order to say print out interrupt E for me. So if you do that, it'll give you the literal address of it'll give you the 32-bit offset of the IDT entry at index E. And then you can just take that address, copy it, and then paste it into the disassembly window up at the top where there's that little offset box and then a place to put things. So you do bang IDT space E in the command window, get the address of the interrupt handler, and then copy that address up into the top of the disassembly window, and then you'll see the disassembly for that command. You left off the E, bang IDT space E. Yep, and as some of you saw, if you just do bang IDT, it's going to show you a few, it'll show you a few interrupt descriptor table entries that don't point at N2S kernel or HAL.dll, just things that point elsewhere. But for now anyways, this is good enough. We're not going to do full analysis on this. Obviously that takes a while. But, some things come to my attention immediately here. One of them is that we're accessing control register 2. So in the intermediate x86 class, we talked about page faults. So we know, first of all, we're at the page fault handler. This is code which should be handling page faults. And then second, from intermediate x86, we know the CR2 register is the address of the memory location which was trying to be accessed at the time that the page fault occurred. So it's like if you go out and try to access memory address 0, and 0 in virtual memory isn't mapped to any physical memory, you'll get a page fault. The hardware will automatically put the address 0 into CR2 so that the page fault handler, when it starts handling this, can say, okay, which memory was someone trying to access? Let me go walk the page tables and see where that should have been mapped. Was it, is it paged out to disk? Is there metadata that indicates that? And all that sort of thing. So anyways, I do go through all this assembly in the TiddlyWiki, and you'll be able to check that out after class. So under the reverse engineering rootkits section, I think it was, I don't know which one it was. Yeah, it was, see, so here's the same code, right? Oh, that's not the same code. There's the same code. So this is that code with the CR2 access and stuff like that. And so I go through and I say, what's the meaning of each of those instructions? What sort of things do we need to remember from intermediate x86 about the stack and the way the stack looks at the time that an interrupt occurs? And then there's actually one extra piece of information that you didn't know from intermediate x86, where when a page fault occurs, there's actually an error code. Well, you may have known there's an error code because this part right here says there's error codes in certain cases, and this one right here says page fault does, yes, have an error code. But what we didn't talk about was the format of this error code for this particular thing. So I copied that in from the manual as well, and that'll describe what's going on. When you see the thing reading this error code and parsing the data, you won't really know what the meaning is unless you go and find out, well, what's the error code mean. So anyways, That's just sort of one example where you could do this with basically any of the things. You can go in with Gmer, you can find things, and wherever it says this point's here, but it can't tell you what's actually at that location, you probably have to go in. All right, sorry, this is my other Windows session. You probably have to go in, find the address, pull up the disassembly, and start actually reading it. And that's why I said this is kind of beyond this class's scope. But in some cases, there really is no other good way than to do that, or just remove stuff. Yeah, you could absolutely just put in any arbitrary memory address here. So you could have just pulled that from the Gmer results, and you could have said Gmer says the point's here, and just go straight to disassembly and WinDbg and paste it in. I didn't do that here because I knew that that's not going to match this. Right? Yes.
Wouldn't you expect to say the same disassembly?
Wouldn't you expect to have the same disassembly if ShadowWalker wasn't there, or what do you mean?
Because I'm not seeing what you're seeing.
Yours is hooked by Toluca right now. So you've got Toluca installed. Okay, so yeah, on some people's systems, if you have Toluca still running from yesterday, here's the reminder here. Yes? Toluca also hooks int E. So if you've got Toluca running, you'll actually see different disassembly at that location. That'll actually be the code for Toluca's kernel driver. Sure. Put it in a Ziploc bag.
Well, I think that's also.
Okay. You do have Toluca running, but you
Same here, I have Toluca running.
Let's see, do I even have it open? Yeah, I have it open as well. So, there you go. Maybe Toluca unloads its driver at some point if you're in, a different tab or something. Could be doing dynamic unloading of it, but not sure on that. But I do know that this is the ShadowWalker code that I'm seeing, but Steve was seeing the Toluca code back there. And again, same thing, had you not known this was Toluca code, or you saw it what Toluca code was hooking, you may still want to go in there and say, what is it actually doing? What's the nature of the changes that it's making in the system? And then you could go in, look at the disassembly, and start teasing out what's going on. All right, so I just wanted to mention that quick. Like I said, I have a bunch of commands at the end of the slides now where you can look for, the IDT stuff. From the intermediate x86 class, we had that one plugin that'll show us GDT and IDT, so you could go look for call gates, for instance, with the GDT command. You can look for IRP hooking. You can look for SSDT hooking. Import address table hooking would be a much more manual process here, so it's not a great way to do that right now, but probably we could find some way to script it in order to make it much more automatic, but I don't have a script at hand at the moment. But there is also then the scripts which were parsing out the callback functions. So for registry callbacks, process callbacks, and thread callbacks as well, I think, and image load callbacks. There's scripts in there, scripts that I got from a blog that can go in there, parse those, and show you what's actually in there. So, like I sort of said when I was making reference to, the reason I wanted to come back to that is just because of, with this detection comparison matrix that I did, where I showed, what can this detect, what can this detect. I said I was, overly generous in this thing, in that I put things down as, yes, this can detect it, even if you had to manually go look for exactly what you want to find. So because WinDbg is so flexible and it lets you go search for the exact memory locations you care about, you can find a lot of stuff with it, but you simultaneously need some more expertise in some cases in order to find things. Well, you wouldn't really know what ShadowWalker does until you, analyze the entirety of the code. So even the worst case is you don't even know what ShadowWalker is, right? If you don't even know what ShadowWalker is, then you're saying, okay, I don't even know what this is doing. Eventually, you'll sort of, let's see here, where could you sort of get help under, where could you see that something's a little weird? So, I mean, the code isn't that big, right? So it eventually comes down to this jump instruction. So it's just, from this jump instruction, it's about 3 clicks worth of code. I don't know how much that is. Yeah, basically what you would see when you're looking at this code is you would see it's doing conditional checks where it's trying to see if memory is in a particular range, and if it's in that range, it goes to the page tables and it starts modifying their values. So from intermediate x86, we had seen there were certain virtual memory addresses that were used by convention for the start of page tables, the start of page directories. And so these C03, even if you just started by, Googling interesting constants, for instance, which is one way to go about analyzing code, just Google that constant, Google this constant, what is it? You would find quickly that these are constants related to paging and stuff like that. And what you would see when you analyze the code is that if memory is in a certain range, which of course is the location that it's keeping its own code, if it's in a range, it goes out and it modifies the page tables, for instance, to mark things as present. And then it does something, and then when it's done, it goes back and it marks it as not present. So you would at least have a sense that this thing is trying to, mark its memory as not present whenever this page fault is not occurring, so that it's basically just will always keep coming back to the page fault whenever someone tries to access it. But, going beyond that, then it becomes an issue of, whether or not you're aware of techniques like Shadow Walker, essentially. So you could infer the existence of something Shadow Walker-esque that's trying to hide memory by marking stuff as, it's marked as non-present. This code runs, it marks it as present, does something, marks it as not present again, and that's probably the degree to which you'd be able to analyze this code, not knowing anything else about Shadow Walker. And similar sorts of things with, other things. Let's say you saw a heap or hook, and you went and you started analyzing the code at that location. You're not necessarily going to be able to pull out and say, this is heap or hook, which is doing this. But if you get a sense of what the instructions are doing, then you can start Googling for sort of what behavior you think it's doing. And then that may or may not lead you to a specific rootkit or specific third-party software.
There's something like, this sort of pattern mentioned,
In this particular case, yes, you could, but you would have to, that would imply you had a collection of known rootkits off to the side, which at that point, you're no different than antivirus, right? So some people do take antivirus and run it across just memory dumps and stuff like that, and that may find this, for instance. But yeah, that's certainly one way you could go about it, and it really then depends on whether you have your own good signature or whether the antivirus has a good signature and stuff like that. Because I will say that antivirus will catch most of these types of rootkits that we have installed. They're all known rootkits. They're proof of concept stuff that's posted on rootkit.com. They even, mark just things that install drivers. They mark those as malicious tools in the antivirus things, which is something Corey and I deal with frequently. We've got just a little program which all it does is load a kernel module into memory, and that's frequently marked as virus by the antivirus stuff just because it came from rootkit.com. So I'm pretty sure they just scraped the site, took any EXEs and said, let's make signatures for those. All right. Anyways, that's all I want to talk about for WinDebug for now, just to say that for some people who had tried to go the WinDebug route, there is this option for local debugging, which you could do on a system without having to reboot it. So you could come onto the system, you could drop Gmer, you could look for stuff, but if you end up with ambiguous results, you could still have the system running, running the web server or whatever it's doing, but you could still be looking at the actual code and analyzing it on the system before you have to take it down, before you try to do any cleaning of the system. All right. So quick review of the stuff, again, that we learned yesterday, since we're running a little ahead of schedule, but that's good because then you're going to get some time at the end here, hopefully, to apply these tools to these machines. These machines need a good looking at, so hopefully we'll have enough time to check them out at the end here. Yes?
So we ran a Win debug in the running kernel. Are there things that are going to be able to hide in there, knowing that, and obviously if we can bootstrap into it and attach the debugger beforehand, then we're going to have better access. Are there things that are hiding that we're not necessarily going to see in the system?
Yes, absolutely, and that won't necessarily be so much because they're targeting WinDebug, for instance, but the important thing to keep in mind, and I call this out in my slides later, is that WinDebug is not an anti-rootkit tool per se, and therefore, so I can do LM for loaded modules. This will, well, I'm going to have to do, 1 second, let me check something. I'm going to reload the symbols, and then I'm going to list the modules. So this is, LM is list modules. It's going to list everything that's installed right now. The issue is here, some of the things which I know are hidden right now, like, let's see if I have this. That's not in the state that it can show me, but the msdirectx.sys and the mmpc.sys, those were 2 kernel modules that were hidden with DCOM. They're not going to show up in this thing's list of loaded modules because this thing just does walk the eProcess structures and walks the loaded modules linked list and walks DLL linked list. So this thing is not going to be able to find things. It's not trying to. It's saying you're just debugging a system. You're trying to work on your own driver. You're not worried about malicious stuff. So this is not meant to get around malicious things. It's just that it can look for certain things. And so if you really wanted, you can manually do the sort of DCOM detection where you could say, okay, here's this list. That's one look. And now let me go out to that PSP SID table. And I'm going to, oh, sorry, PSP SID table was, sorry, that was for loaded processes. But there's other things you can do like searching for specific signatures related to the data structures that are in this linked list, and you could say, okay, search memory, found all these data structures, and now let me, take those links, those loaded modules versus these loaded modules, compare the list, and see if there is anything hidden. But by default, this will definitely not show you any DCOM stuff. It won't show you anything about hidden files or anything like that because it's not meant to look at file stuff. It's meant to look at memory. So yeah.
Well, what would be the distinction between running it as we are now versus running it on a cold boot?
Right. On a cold boot, I'd say the distinction would be that for something like, let's say, Futu, if I run this on a cold boot, I can issue a particular command, which that's a good reminder to me that I need to put this command in. 1 second. And then make sure I mark it. So if I run a particular command, it will actually interrupt, it'll cause a breakpoint every time a new module is loaded into memory. So for some of these things where they load into memory and then they, for instance, unlink themselves or unlink other things, you would have seen that it's loading at load time. You could have examined all of its code and everything else. You could parse the PE headers, go to the image, the address of entry point field of the PE headers. See, that's where the code starts, start analyzing it. But the point is, if you let it run, then after that, then it's going to immediately hide itself. You're not necessarily going to know where it is. So it really becomes an issue of, stopping every instance of loading of drivers. In the heap for hook case, it gets really nasty in that you probably have to intercept all accesses or all allocations of kernel heap, essentially. So because the thing, it loads up, so you would see it at load time, and then it takes its own code, allocates a chunk of heap space, and copies itself into the heap, and then unloads that driver, so it's just not there anymore. But then, it's sitting there in the heap memory. And so the problem is, right now, if I try to find out who allocated that heap memory, who copied that code there, there's really no way that I can answer that question.
Okay.
But if I do it on a cold boot, I can intercept every single heap allocation, and I can, create a list of, here's the drivers that allocated this location and that location and that location. And then I can eventually tie it back to say, okay, it was that driver that popped in and then popped out again. And so it's really just a question of getting yourself in and being able to watch every event as it occurs before the attackers actually get control. It's sort of the same issue that we had with those callbacks that we talked about yesterday. I said, if security software gets there first, and if it says, you know, I want to find out every time something loads into memory, then it kind of wins. And if the rootkit gets there first, and it says, I want to know every time someone's loaded into memory, then it wins. Same issue here. The debugger, as long as it started early enough, then it can really stop before the kernel's loaded and anything else is loaded. It can't stop before master boot record and that sort of thing. But once the OS is loaded to the point where the kernel debugger can talk out, then it can see everything after that point. Yep.
So when you load WinDebug, isn't it just loading the device driver?
Right, exactly. So when you load WinDebug, and even on a cold boot, it's still loading a device driver. It's loading it as early as possible, but it's still has to load that. Now the thing is, it actually does load it before. Well, I shouldn't say that if I'm not sure. I believe it loads it before the kernel. I mean, certainly, I know that I see the kernel load events occur when I'm doing a cold boot, but that doesn't really jive with my notion of rootkits. But anyways.
So I was thinking that if you do it locally, that it's loading the device driver, but if you do it during cold boot, then you're actually just enabling the hooks that are already built into the kernel.
That could be the
I
case.
think, I'm not sure.
Yeah, that's reasonable. It's worth looking into, actually.
Eric, you probably.
Can you use reload document to do
Dot reload. So it's not reloading the modules, it's actually reloading the symbols. In all of your VMs, because I had already had WinDebug installed and I uninstalled it so that you would have to install it if you wanted to use it. But all of your VMs, if you go to File Symbol Path, they will probably already be filled in with the appropriate Windows symbols path. This is just the URL so that you can download symbols from Microsoft so that this thing knows what the names of modules are, knows what the functions are within those modules, etc. So does everyone see that in their thing? Yeah. So that was already there. On a new system, when you're putting this on, you know, the system you got sat down in front of, you have to know that you have to put that in there. And it's going to be reaching out to the internet and pulling stuff down. If it doesn't have internet access, you potentially have to bring along a symbols file on a DVD or whatever in order to tell WinDebug where to find that, so you can help you understand the system better. All right, so that was WinDebug, doing a local debug, and talking a little bit about the benefits of doing it on an actual reboot. So just to quickly recap what we talked about yesterday, in terms of stuff you already had a sense of from other classes, potentially, we talked about IDT hooking, and we said that IDT is just a big array of these interrupt descriptor gates, which are far pointers. They've got a 32-bit offset and a 16-bit segment selector, and the segment, though, always pretty much selects a segment which starts at 0 and goes to 4 gigabytes. So really, in typical usage, the 32-bit offset is just the virtual memory address. Second, we talked about call gates. So we said there was a call gate installed in the thing, and how the call gate looks very much like an interrupt gate. It's got a segment selector and an offset, and it's really just specifying here's a target address inside the kernel space where the kernel sets it up so that user space can call this call gate and it'll transfer control to the kernel. Basically a way to allow that inter-ring transfer. And we talked about import address table hooks, which we had seen briefly in the Life of Binaries class. We said every P file has, if it imports something from other modules, it's got an array of these structures, one per thing it imports from. So here's a simple example where you've got some kernel module, it imports from NTOS kernel, and there's an image names table and an image address table. Initially, on disk, they both point to the same thing, but then in memory, when the OS loads up the binary, the import address table gets pointed to the function pointers for the things which are actually imported. And the whole point of the IAT attack is that the attacker just comes in, points those IAT entries at the zone code, and starts man-in-the-middling. And we also talked about inline hooks, where it's really just putting things like jump instructions or other small changes. You overwrite some code, you copy the code that got overwritten off to the side. All right, so that was stuff that we had kind of seen through other classes. And then out of things that we hadn't seen yet, there was, this covered a couple different types of things, right? So we know that there could be import address table hooks. There could be IIT hooks, and we'd seen that, and there could be inline hooks, and we'd seen that. IDT, IAT, inline, whatever. But what was new here was covering this entire process, and the fact that, you know, one other path that's more commonly used now in order to go from user space to kernel space is sysenter. And we saw, okay, there's specific models. There's model-specific registers which are used to say, here's the target. The IA32 underscore sysenter underscore EIP is the EIP where they want control to transfer at such time as you call syscall. So, or sysenter. So that MSR is set up to point at this normally, but if an attacker comes in, they can point it wherever they want, and then they'll functionally have met in the middle this control flow from user space to kernel space. And we said that once you get to one of these functions, what they're going to do is they're going to say, okay, what thread is running right now, and where is that thread service table pointing? So it'll either be pointing at the shadow table or the normal table. And in each of these cases, these tables had 4 entries, and so we know down here in user space, when you're calling a system call, you put EAX equal to the syscall that you want to call. So you say EAX equals 112, for instance. And so this guy here parses the EAX and says, okay, 112, well, bits 13 and 14, those are 0, so I'm going to go to, for instance, the chair. So I'm going to go to the 0th entry of this right here, and then this has a service table entry which points at that table right there, which has all of those function pointers in it. So the 112, it's, you know, the 0th entry of this, and the 112th entry of that, and then all of this table over here is always supposed to point into N2S kernel. So those are a bunch of functions which are supposed to be implemented in the kernel proper. As opposed to when something is using GUI functionality, GDI, that we talked about yesterday, that has an alternate path. This was GDI32.dll. It comes in, it ends up at these same things. When they're parsing EAX, instead it'll be something like 1112E or something, or 112E, something like that is what we saw yesterday. And that initial one says, so first of all, it would be consulting the thread information. The thread information would say it's pointing at this instead. So for anything that uses GUI functions, its thread information points here. Anyone that doesn't, they point here. Right, so 112E would say index 1 of this, and then index 12E of this, and then those would point over to win32k.sys, which is the thing which implements the kernel side of the GUI components. So we said you can actually hook, you know, either of those tables. Call that the shadow SSDT, call that the normal SSDT. In either of those cases, you can change those function pointers to point at the attacker code. And we said in some cases, like Black Energy Rootkit, it actually says on a per thread level, it'll say, okay, well, this thread is not pointing at that, not pointing at that. It's actually pointing at some different structure over here, which potentially points at a different function pointer table. We also saw yesterday, and we're not going to see a tool which actually does this until the end of the day, but I briefly described that in the case of heap or hook, in those 4 entry tables, we said that there can be, if IIS is installed, there can be a 3rd entry here. Normally that's not installed on any of our machines anyways. So that's usually going to be empty like on the top, but heap or hook calls this KEAD system service table, and when it does that, it gets a new structure right here, and that structure then points out to a table which has some number of function pointers in it. And we said heap or hook uses this as a sort of user space to kernel space command and control mechanism. So it says, here kernel space, I've got a new file that I want you to hide. Here's the name of the file, and it's going to call, you know, command 2 or something like that. All right, so that was sort of You saw this was different levels of STT hooks, but really you can kind of hook anywhere along this path. All right, then we talked about IO request packets. And the key point here was that there were two different ways that an attacker can interpose on these, man in the middle of them. Way one is to just create, he inserts. Way one is that he loads up a kernel module. His kernel module is going to get a driver object associated with it. And then he's going to create a device object and say, I want that device object to be here, or I want that device object to be here. Right? So a driver creates device objects and puts them into the chain. In that way, he's registering himself as a filter driver. It's because he's sort of filtering commands coming up and down the stack. That's way one. Way two is, instead of even bothering to put yourself into that chain, just figure out where there's something at the level that you want to be at and go into this major function table, which is an array of 28 function pointers tacked onto the end of these driver objects. And these basically say, here's the function which implements the handler for create IRPs. Here's the one which implements the handler for directory control IRPs. And so you can just put himself in here and point these function pointers out to the attacker's code, and then he'll be called whenever a, let's say he's in the keyboard thing, whenever a read IRP is coming down. So the read IRP comes down, gets to the hardware says, oh, here's that keystroke you were looking for, and then it comes back up the line calling the completion routines for anything that asks for a completion routine to be registered. And so an attacker could see that an IRP is coming down by hooking the read major function. Like say he's right here. Say there's the read entry right here. He can see when read is coming down, his code gets called based on the function pointer here, and he can set up and say, okay, when that's coming back up the stack, I want to hear about it, so here's my completion routine. Call me back when you're done with the read, so that I can see the actual data that has been read, in this case a keystroke. All right, so that was IRPs. We said these were the different types of IRPs. We saw that this directory control was relevant to Stuxnet as well as key for hook, which is installed. Because when it's doing a directory control thing, that's the thing which is used to list files within a directory. So if you filter on that, you can remove your entries from the file system. All right, we talked a little bit about DCOM as well. We said that, in the simple cases, it's things like removing things from linked lists. And I gave 3 examples of where this could happen. One, it could be hidden processes, which will hide things from task manager level viewing. So when task manager calls a function to get a list of what programs are running right now, that function it calls basically just walks this list in order to find out what's running. But if an attacker takes the forward link and instead of pointing to this process, he points it over that process there, and he points this one's backwards link to that there, then this thing is just not included in the list, and so when someone walks it, they're not going to find it. Basically, the exact same thing can happen for loaded kernel modules, which is what we have hidden in here. There's 2 kernel modules that are hidden with this technique. There's a different data structure used for them, but it's the same idea. You've just got a linked list and you move yourself. And the exact same data structure that's used for kernel modules is used for user space VLLs. So in either of those cases, you can just remove yourself. Well, I don't believe there is other housekeeping they have to do. In some sense, you can think of this list like sort of, you can think of it like, well, I kind of think of it like useful information that the kernel would like to have at its fingertips if it ends up needing it. But like I said yesterday, fundamentally, it's not something that's required to actually schedule the process. So the scheduler uses thread level information. So there's going to be various pools of these threads, and they're going to be at different priority levels. And we say these threads get scheduled first, and those ones get scheduled later. And the thread information is what's used to actually run processes. Now, if you're wondering if when a hidden process, maybe if the hidden process calls some function, and if that function would have looked at this list in order to find this information, and then wouldn't be able to find it. I don't think that's the case because, as this picture sort of shows, for whatever the current running thread is, the current running thread still knows where to find an example off the top of my head where some function would be querying this data structure. But if you think of it like whenever the hidden process is running, it's unlinked from the list, so it can't find information about anything else, but it can still find information about itself. So no functions are going to die and fall over on it because it'll still be able to get to the data structure through this path. But, you know, if the hidden process wants to go find other processes, then potentially it would have a problem. So that's an interesting question, actually. I should see what happens when I hide Task Manager if it suddenly loses the ability to see processes. I kind of doubt it. Any other questions, sorry, as we're going through IRP stuff, SSDT stuff, inline hooks, anything like that? All right. And so I just talked about the list examples of this. There's also examples like token elevation, process privilege elevation, where you go directly to the data structure that holds your privileges for this process, and you just elevate it and say this is now a system level process that can do whatever it wants. So decom just means instead of using APIs, you've gone and you've reverse engineered things, you understand how they work, you go directly to those data structures. You find some way of finding the data structures you care about. So in this case, he's saying, hey, I know how to find that data structure, and from that I can get that link, and from that I can get that link. And so you need to have, the attacker needs to have some way to find what they're looking for, but once they have that, then they can go and manipulate the data however they want. All right, and then I think this was the last thing we covered yesterday, the OS provided callbacks or notify routines, whatever you want to call them. And we said these were monitoring functions. These are things where they'll tell you when certain events are occurring. And they're trying to push developers to use these types of things rather than those unsupported mechanisms like hooking the SSDT, putting inline hooks in the kernel and stuff like that. So for security programs which want to find out every time registry is being edited or every time a process is being created, they can find it using these methods. The flip side of the things is that if a rootkit gets installed first, and if it, for instance, has a callback on the load image notify routine, that means it can see every single thing that gets loaded into memory. It can change it. So there was one example that we talked about where this POC hybrid hook one, it says whenever something's loaded into memory, I want to take a look, and then it'll scribble over its import address table if it's importing something the attacker wants to hook. But there's other things like, let's say Rustock, for instance, has a process notify routine. Let's say it sees that your antivirus semantic, let's call it semantic.exe, loads up. It sees every time a process is loaded, it can see the name of the process and can just immediately terminate it, right? So if you get in there first, then you're just killing processes, you're scribbling over them, changing them, that sort of thing. Exactly. So when you call one of these functions, so you say CM register callback, that's a function you call, and you give as one of the parameters, here's the address where I want to be called later on, right? So then the OS puts you into a list of a bunch of addresses it's keeping so that when an event occurs, it goes, calls that one, calls that one, calls that one. And it just kind of walks down the line and calls everyone who's asked to be called back. And so yes, you're correct there. There can be attacks where they mess with the list. And actually, I was looking at this last night. Let's see if it's still open. I don't think it is. So like I said, I was trying to see exactly what each rootkit does by itself. And for some of the more advanced ones, like some of the ones that aren't just like proof of concept where they're doing one technique, I'll admit that I haven't, looked over all of their code and seen every single thing that they're doing. So on the notifiers, I was noticing last night when I only installed Keyfor Hook, there's these shutdown notifiers where there's actually a lot of these naturally. So just on my clean system, I look and I see a bunch of things. But it looks to me, so these ones right here where they all have the same address, these are Keyfor Hook things. And I think I'd have to confirm it, but it looks to me like there were a bunch of existing shutdown notifiers. He4Hook came in, and it overwrote those with its own function pointer address. And I think that's a great attack. That's the way to do it, right? So you don't want, the security software or something like that. I mean, it all really depends on whether the security software can stop you or not in the first place. But if they're not stopping you, or let's say you just have something like an exploit, a kernel mode exploit, if you have arbitrary write permission, you can go in and, point the callbacks for some security software at a return instruction, right? You can say, I want the function to be called to be that address, and that address just happens to correspond to a return instruction so that the security software's callback always just returns. It's functionally blinded, stuff like that. But it, like I said, it looks to me based on, so it was really based on these device object things right here. Those device object things didn't change between the clean system and the dirty system. So these used to point at legitimate system drivers like mup.sys and other things. But post He4Hook, I could see that, all those addresses got changed to the same He4Hook memory space looking address. But those device objects didn't change, so that was kind of interesting. So yep, attacker can go in and mess with the list as well. So there can be things that are registered to find out when events occur, but the attacker could go in and put himself so he's the first one that hears about it, or he can go in and remove security software and stuff like that. But of course, it all depends on when the attacker is executing relative to security software, what his permissions are, whether he's being intercepted, all that sort of thing. All right, so I just kind of glazed over this, but if you go to these sites, I'll try this maybe at the next break. For some reason, it wasn't working on my VMs anymore, but at these URLs, there's two little Windebug scripts which will parse those lists. And so therefore, you can actually go in, read the script. They're pretty simple, and you can see they're keying in at specific symbol names, and you can go to those symbol names, and you'll see the function pointers in the list. And so specifically, it's actually just an array on WinXP. It's a list in like Win7. And yeah, so we left it with VirusBlock Ada has pretty good detection of these callback mechanisms. You've got a bunch of security software in here. You've got some legitimate things like cal.dll, ndis.sys, etc. But then you've got stuff where they have unknown handler, which I'm pretty sure are associated with He4Hook. All right, so any questions on the stuff that we went over yesterday? That was our quick review there. Inline hooks, IAT hooks, IDT hooks, call gates, blah, blah, blah. No questions? Anyone on the phone have any questions? All right, then I'm going to go on.